All right, so for this experiment, what we're going to be doing is we're ultimately going to be determining the molar volume of hydrogen gas at STP. STP, as we know, is 273 Kelvin or 0 degrees Celsius and 1 atmosphere of pressure. Now, in order to figure this out, what we're going to do is we're going to do a single replacement reaction with magnesium ribbon and hydrochloric acid. And that's what's going to produce our hydrogen gas. And then we're going to measure the volume of the hydrogen gas at this temperature and pressure. We're not at STP. It's not 0 degrees Celsius in the lab. And so we'll figure out the volume of the hydrogen gas at this temperature and pressure, and then we'll do calculations to figure out, well, what would that volume be if we were at STP, and then compare it to what we know it should be. All right, so the first thing that we're going to do is we need to record the pressure of the room. So what I have here is just a barometer hooked up to our lab crust. I have our units in millimeters of mercury. And so this is reading 749.85 millimeters of mercury. So we're going to record that in our lab notebook. Okay, so that is our room pressure currently. We also need to know the temperature of the room. So I'm just gonna take a thermometer, read the temperature here. It's reading at 20.8 degrees Celsius. All right. Then what I need to do is I need to measure the mass of the magnesium ribbon. So the magnesium ribbon's pretty small. Let's see here. And the reason it's small is we're going to be collecting the gas inside this uniometer. The uniometer can only hold 50 milliliters of gas. So I don't want to use too large a piece of magnesium ribbon such that I generate more than 50 milliliters of hydrogen gas. I need to keep my volume of hydrogen gas contained inside this uniometer. Now, because this piece of magnesium ribbon is so small, I'm not going to be using our regular balances. Instead, I'm going to be using our analytical balance. The analytical balance is more sensitive. It gives me another decimal place. So if I were to use the regular balances, I would only end up with one significant figure for the mass of magnesium, which would then limit my significant figures for all of my calculations, and I don't want that. So I'm going to be using the analytical balance so that I can get another decimal point and now have two significant figures. These are more sensitive. You can see that they have a lid because even just airflow is enough to change the mass. So I'm going to zero balance magnesium ribbon on, and it has a mass of 0.027 grams. Okay. So I have the mass of my magnesium ribbon. I also need to measure out the hydrochloric acid that I'm going to use to react the magnesium ribbon. We're going to be using 3 molar hydrochloric acid. The hydrochloric acid is in excess. The magnesium ribbon, that's our limiting reagent. So that's why we need a precise mass for the magnesium ribbon. The hydrochloric acid, we need approximately 15 milliliters. If you're a little bit over, a little bit under, it's not a big deal because again, this is our excess reagent. All right, so the reaction is going to take place inside this uniometer so that the gas is trapped. So how am I going to do that? What I'm going to do is I'm going to use a piece of copper wire and I'm going to wrap it around the magnesium ribbon to secure it to the end of the uniometer. And then I'm going to use the stopper here to plug the uniometer so that the reaction can take place. So I'm going to take my magnesium ribbon and I'm actually going to fold it in half so that I can more securely wrap it. Just kind of go around the ribbon. Again, the better that you wrap this. I'm going to make a little hook at the end of my copper wire. So the reason I'm going to do that is because this is going to secure the magnesium ribbon at the top of the UDiometer. So the reaction, I'm going to do this reaction in the UDiometer, but then over this beaker filled with water. So the clamp here is going to secure the UDiometer. Okay. So what I want to do now is I'm going to add the hydrochloric acid to the UDiometer. So I'm just going to pour that in. So the hydrochloric acid is going to stay at the bottom of the UDiometer. I'm then going to fill the rest of the UDiometer up with deionized water. Now, hydrochloric acid is more dense than water. So the hydrochloric acid is going to stay at the bottom and the water is going to stay on top. It's really important that I completely fill the UDiometer. I don't want any air inside this UDiometer because then that would increase what I would think would be the volume of hydrogen gas. I want any gas that's going to be inside this UDiometer to just be hydrogen. So now what I'm going to do, I'm going to place my magnesium ribbon inside the UDiometer, and it's not going to react yet. Again, the hydrochloric acid being more dense is down at the bottom. So I'm just going to secure my magnesium ribbon and place the stopper. And a little bit of water came out, which is a good thing. That tells me there's no air inside the UDiometer. It's completely filled with the hydrochloric acid and the water. So now what I'm going to do is I'm going to invert the UDiometer and place it inside my beaker. And when I invert it, the hydrochloric acid that's here is now going to travel to the bottom where my magnesium ribbon is now trapped. Then a reaction will occur and we'll see the bubbles form, which is the formation of hydrogen gas. So there's a hole in the stopper. And that hole is important because the water needs somewhere to go. Otherwise, the pressure from the hydrogen gas would cause this to explode. So I'm going to cover that hole with my thumb just to make sure that no air or anything gets inside the UDiometer. And I'm going to invert this and put it into the beaker of water. And then I'm going to clamp this so that I don't have to just keep holding it this whole time. Now you should notice that the position of the UDiometer is important. I don't want the bottom of it to touch the bottom of the beaker because again, that wouldn't let the water get out and that would cause a buildup of pressure, not a good thing. So what's happening now is the hydrochloric acid that was at the bottom of the UDiometer, again, being more dense than water, now it's sinking back to the bottom, but the bottom is now here. So as the hydrochloric acid starts to make its way down to where the magnesium ribbon is, we should start to see bubbles form. And it's a pretty vigorous reaction, this single replacement reaction. So this is just going to take probably another 30 seconds to a minute for the hydrochloric acid to get down to the bottom and react. So hopefully you can see the bubbles of gas that are being evolved from the reaction. As the hydrogen gas floats to the top, it then displaces the water into the beaker here on the ring stand. So we need to let this completely react Again, it's important that all of that magnesium ribbon reacts because that's our limiting reagent. So the mass of the magnesium ribbon, that's where we're going to be starting all of our calculations from. So I need to ensure that all of that magnesium ribbon has reacted. So we're going to let this go until we see the bubbles stop evolving, and even then give it another 5 more minutes, just to ensure that all of the magnesium ribbon has reacted with the hydrochloric acid. So as you can see, the reaction produced approximately 26 milliliters of hydrogen gas. So the hydrogen gas is up here. Here's the rest of the water and any extra hydrochloric acid down here at the bottom. I do need to record not just the room temperature, but also the temperature of this water. And the reason why I need the temperature of the water is that there is water vapor mixed in with my hydrogen gas. And I'm gonna need to use Dalton's law to subtract out the vapor pressure of the water so that I can determine what the pressure of just the gas is. So I need to know what the temperature of this water is, because the vapor pressure of water is gonna change depending on the temperature. So I have my thermometer here in the beaker. The water is a little bit warmer than the room temperature. And so this is reading 21.5 degrees Celsius. So I'm gonna record that as well. Now, I said approximately 26 milliliters of hydrogen gas. I do need to record a precise volume of the hydrogen gas, but I'm not gonna do it right here. What I'm gonna do is I'm gonna transfer my UDometer into this graduated cylinder. So why am I gonna do this? I measured the pressure of the room. I can't put my barometer inside the UDometer to measure the pressure of the gas. So I need to know that the pressure of the room is the same as the pressure inside the UDometer. Now, how am I going to know that they're the same? Well, the atmospheric pressure that's pushing down is affecting the level of water in the graduated cylinder. So if this level of water is at the same height as the level of water inside the UDometer, then I know that their pressures are the same, and then I can record the volume of the hydrogen gas. So this is a little awkward to try to do, but what I need to do is I need to take this UDometer and I need to put it inside this graduated cylinder. I am not interested in the volume of the graduated cylinder. I just needed water inside of it. I just needed a long tube. I do want to use my thumb again to cover the hole because I don't want any outside gas traveling inside the UDometer. Yes, there was hydrochloric acid, but it has been diluted in this beaker of water, so it's safe for me to put my hand in here. And I'm just gonna cover up that hole there and transfer this inside here. And then what I wanna do is I want to get the levels to be the same height, and when they're the same height, that's what I'm going to record the volume of the hydrogen gas inside this UDometer. Now, our UDometer is marked more precisely than our thermometer is, so we are going to have more significant figures here. So this is reading 26.18 milliliters. So now I have the volume of the hydrogen gas. I'm going to use that and all of the other pieces of data to calculate what the molar volume of hydrogen gas would be if we were at STP.